Dear students, we will continue this topic, basic theorems of Boolean algebra. In the last class, we have seen 9 theorems, and we even know that the basic postulates of Boolean algebra we are using to define the basic theorems of Boolean algebra. So let us continue from 10th one. Okay. So the chapter is Boolean algebra, second chapter, class number 6. Okay. So here, as usual, each and every theorem is having name, and till 9 we have seen so many names associated with the theorems. And here, likewise, we are having names for the 10 and 11 as commutative laws. Okay. So these two are commutative laws, and these two are identified as associative laws. So we are all familiar with the commutative law and associative law. Even in Boolean algebra also it holds good. So here commutative in the sense we are interchanging the variables. So here x plus y is nothing but y plus x. Likewise x into y equals to y into x. So here our operator, here we are having AND operator. So in the associative law we are having 3 different variables. Of course, in the last class I told you till the 9th theorems, whatever we have seen up to 9th, we had only one variable in the statements. So now from 10th onwards up to 18, okay, so we are having overall 18 theorems. So from 10 to 18 we are having either 2 different variables, or in some cases we are having 3 different variables in a theorem. So here in these 2 commutative laws we are having 2 different variables. When it comes to associative law we are having 3 different variables. Okay. So we are having 2 methods to prove the basic theorems of Boolean algebra. One is proof by perfect induction, where we are considering all possible values for the variable, and the alternative method is to go for using a table. Okay, so it is nothing but using the truth table. So whichever the method we are taking to solve the given theorem or to prove the given theorem, finally we will see the gate representation or the circuit diagram for the theorem. So it involves the diagram for LHS part and the circuit construction for the RHS part. So let me take up the first one, 10th one. So there it is x plus y equals to y plus x. So here number 10, the statement is x plus y equals to y plus x. Method 1, perfect induction. So let's continue. Consider first x equals to 0, then we will say x equals to 1. So here it is not necessary that you have to take the variable x only. Instead of x equals to 0 one time, another time as x equals to 1, you can take the variable y also. So you take any one variable. So whether it is having 2 different variables in a statement or 3 different variables in the given theorem. So take any one variable, consider 0 for that variable one time and 1 for that variable another time. So no need to take the other variable also. Suppose if there are 3 variables, take any one variable, leave the other 2 variables. So taking only one variable, assuming 0 for it one time and 1 for it another time, it is enough for us to prove the theorem. Suppose if we get LHS equals to RHS. Okay, so here I am taking x as 0, substitute 0 in the given statement. Okay, so x plus y is nothing but 0 plus 5, that side it is y plus x, so y plus 0. So now what we can do, we can even use the results of previous theorems. Okay, so here the postulate is enough for us. So it's an OR operation. So it is nothing but y. Okay, so that side also y plus 0 is just y. So we are considering our operation plus we are using the result of previous theorem, one of the previous theorem. So what is that result? So we know already from the properties of 0. Okay, so 0 plus x equals to x. Okay, so this one we already proved in the beginning. So we are using that result to say 0 plus y as y and y plus 0 as y. So here we are having LHS equals to RHS. So call it as 1. Now when x equals to 1, substitute one value in the given expression or the theorem. 1 plus y equals to y plus 1. So here again we will use the previous theorem, the properties of 1. So already we know that 1 plus x equals to 1. So here in place of x we are having just y. So 1 plus y is 1 only. Y plus 1 is 1 only. So here what is happening again, we are getting LHS equals to RHS called as 2. So I already told you, finally we have to write the conclusion. Okay. So what you can say from 1 and 2, theorem is proved. Okay, that is the conclusion. So in both the cases we are getting LHS equals to RHS. So it's about the proof by perfect induction. Let me go for using truth table. So here we are having two different variables, x as well as y. So overall 4 possible cases, different possible cases when you consider the binary values for the variable x and y, because the variables themselves they are binary type variables. So the possible cases we are going to write from 0 0, then 0 1, 1 0 and 1 1. So x plus y, so it's an OR operation. So only in this case, okay, it is 0. In the remaining cases it is 1. Okay. So now even when it is y plus x, OR operation, the OR operation property says that if both are 0, then only it is 0. So whether it is x plus y or y plus x. Now it is going to be 0 as both are 0. So in the remaining cases, here also we are going to get 1, 1 and 1. So these two columns are required for us now. So x plus y column 0 triple 1, y plus x column 0 triple 1. So both the columns are identical, or you can say both are same. So theorem is proved. So here also you write the conclusion finally. So here the columns x plus y and y plus x are same, hence it is true. Okay, so conclusion we have to write. Then the gate representation for this statement x plus y equals to y plus x for LHS. Okay, so for LHS, plus means it's an OR operation, showing two inputs for an OR gate. Okay, so first say x plus y, the first signal is identified as x, the other one as y, so it is x plus y. If you change the signals, okay, so first if you take the signal y, then x to the OR gate. Okay, so it is what? Y plus x. But still, we are going to get same results for x plus y or y plus x. So this circuit is equals to this one. So whatever result we are going to get for that one, x plus y, the same result we are going to get for y plus x. Okay. So we'll move for the next one, other commutative law. So instead of OR operation we are having AND operation. So x into y equals to y into x. So in this only I will go for some changes. So theorem number 11, x into y equals to y into x. So again select any one variable, either x or y, assume 0 one time and 1 another time. So let it be say x equals to 0, substitute 0 in this given theorem. So 0 dot y equals to y dot 0. So again from the properties of 0, when 0 is ANDed with a variable, answer is going to be 0. So properties of 0. So we already proved that theorem in the last class. So we know that 0 into x equals to 0. So that's why whether it is 0 into x or x into 0, we are going to get 0 as the answer. So using this one, so the previous result, we can say 0 into y is 0 and here also it is 0. So LHS equals to RHS. So when if we are considering x equals to 1, so we are going to use the property of properties of 1, or you can say the theorem where it is identified as properties of 1. So when 1 is ANDed with a variable, what is the answer? The variable itself. Okay. So now substitute this value 1 in this expression of the theorem. So in place of x, it is 1. The variable y equals to the variable y and into 1. So properties of 1. So as I told, and the value 1 is ANDed with a variable, answer is going to be the variable itself. Okay. But here when the value 0 is ANDed with a variable, answer is going to be 0. So here when the value 1 is ANDed with a variable, answer is going to be the variable itself. So because of the properties of 1. So 1 into y is y. That side also y into 1 is y. So again LHS equals to RHS. So the final conclusion from the equations 1 and 2, the theorem is proved. So now we will take up the method 2. Okay. So again there are 4 possible cases: 0, 0, 0, 1, 1, 0, 1, 1. But we are having AND operation this time. Okay. So AND operation says that answer is going to be 1 when both the variables are 1, or else answer is true when both are true here in this case. So here there are 2 variables, so both are 1, here is the case. So here we are going to have 1 for this expression. The remaining cases it is 0. So when the AND operation is there, whether we are having x into y or y into x, it is going to be same. Again the value is 1 if both x and y are 1, otherwise it is 0. So again you are going to get same result. So as we got for the x into y. So again you write the conclusion. Here are the columns x into y and y into x are same. Hence it is proved. So theorem is proved. So what about the gate representation? Instead of OR gate, we have to use the AND gate. So instead of plus, put a dot, or else you can just write x and y. It's understood. It's an AND operation. Okay. So AND gate we have to use here. Here also, just change the variables. First we have taken x. Here we have taken second time as x. Okay. So it's yx. It is xy. So both are identical. Both are same. This is for RHS. This is for LHS. Okay. So this is about the commutative laws. So both the 10th and yes, it is 10th and 11th. So next two are identified as associative laws. So first I will take up the 12th one. Okay, where we are considering the OR operations. X plus within the bracket y plus z is going to be same as within the bracket x plus y, then ORing with variable z. Okay. So again I will show you both the methods, prove by perfect induction method and using the truth table. So here in the 12th theorem we are having three different variables. So this is the first time in a theorem we are having three different variables. Okay. So when it comes to this method 1, so again as I told, take any one variable x or y or z. So take any one, have 0 for that variable one time and the value 1 another time. So in both the cases, if you get LHS equals to RHS, we can say from 1 and 2 the theorem is proved. But when it comes to truth table, now we have to show all the 8 possible cases because there are 3 variables. So 2 to the power cube. So 8 different possible combinations of zeros and ones we are going to get. So for all the cases we have to check for whether this LHS column, okay, is identical with this RHS column here in the truth table. So first go for the proof by perfect induction. So theorem number 12, x plus in the bracket y plus z, which is going to be equals to with x plus y in the bracket plus z. So proof by perfect induction. Method 1. Let x equals to 0. Substitute this 0 in this statement. So 0 plus y plus z equals to 0 plus y plus z. So wherever we have x, we have to fill with 0. Okay. So now again we will use the properties of 0. So the theorems which are already proved again we are using. So now here this part you can see it as x. Okay. So this one is 0. So 0 plus x, the properties of 0. Okay, starting to theorems. So 0 plus x or x plus 0 is x only. So in the same way, what you can say now, this part when it is ORed with the another part, okay, ORed. So OR in capital. So 0 is ORed with this one, y plus z. So it's an OR operation. Okay. So now it is 0. Now it depends on this part. So 0 plus x is x, we already know. So in place of x we are having some expression. So 0 plus that one is going to be this one only, y plus z. So or else we can see in another way. What is that? You can see this part as 0 plus y plus z. So in that way, so it is already 0. You can leave this one. Now everything depends on y plus z. Okay. So anyway, you want to write the reason, you can write the reason using the properties of 0, where 0 plus x equals to x. So now what happens this one, it is y plus z, that side, okay, 0 plus 5, properties of 0. So we know again the same theorem we are going to use, this theorem, 0 plus x equals to x. So we are using this one here, again we are going to use in this case also. Okay, so 0 plus 5 is y, the other side it is z. So y plus z equals to y plus z. So it is nothing but LHS equals to RHS. Let it be 1. So now x equals to 1. So we are going to use the property of this one. 1 plus x equals to x, property of 1. So when 1 is odd with a variable, the answer is going to be 1. Okay. So we use this one, this property now. So now substitute this 1 in this statement. So 1 plus of y plus z equals to 1 plus y plus z. So now this y plus z is odd with this 1. So in place of x we are having y plus z. So 1 plus x equals to 1. So 1 plus this part is nothing but going to be 1 only. So 1 equals to, on the right hand side, 1 plus y equals, sorry, 1 plus y plus z. So 1 plus y is 1 again because of this one, property of 1. So 1 plus y is 1 plus z. Okay. So this side it is 1 as it is, we continue with the value 1. Then 1 plus z, again we will make use of this one, the same property of 1. 1 plus x equals to 1. So 1 plus z equals to 1. So again what is that? LHS equals to RHS. Second. So the conclusion from 1 and 2 theorem is true. So now to table. So all possible cases, how we are writing, starting with all zeros. Nothing but it's a binary equivalent of decimal value 0. Then binary equivalent of decimal 1 is 0, 0, 1. Next, this 0, 1, 0 is a binary equivalent of the decimal value 2. Now like this, if you go on writing the binary combinations, then it is going to be next 0, double 1, then 1, 0, 0, 1, 0, 1, 1, 1, 0, triple 1. Next, so it's about 3 different variables case. So we have written the possible, all possible combinations of zeros and ones for the given 3 variables x, y, z. Then this is a theorem. First we will go for this y plus z because of the bracket. So we will follow the precedence rules. So when we are having logical operators, first preference is for the not operator. Suppose if we have not operator, so we don't have not operator, then the precedency or the priority is for the AND operation. Then lastly we are having priority for the OR operation. Suppose if brackets are there, we have to consider the part of the expression within the bracket. Okay, so here we will consider this one first because of the bracket, y plus z. So we will write that on y plus z. So then here for y plus z, these 2 columns we have to refer y and z. So it's an OR operation. So it's going to be 0 when we are having both as 0. So here we are going to have 0. In this case also we are having both y and z as zeros. So 0. And in the remaining cases it is going to be 1. So next what we do? We will go for x plus with this result y plus z. So now I will write that one, x plus of y plus z. So already we are having x column, individual column, and this is y plus z. So these 2 columns. Okay, so this is y plus z and this is x. So between these 2 we are having OR operation. Okay, so between these 2 columns, suppose if we get both as 0, then it is 0. So in all the remaining cases it is going to be 1. Now we will shift to the RHS part of the expression. So here again we consider the part of the expression within the bracket. So x plus y we consider first. So the column x and y, and it's an OR operation. Okay, so both are 0, then only it is 0. Here also it is going to be 0. And on all the remaining cases it is going to be 1. Next we will go for ORing with variable z. So again an OR operation. So x plus y column is here and the column z is here. So between these two columns, if both are 0, then it is 0. Otherwise it is going to be 1. Okay, so finally we need these two columns, this one and this one. So if you get both as same, okay, so now both the columns are same. This one, this is LHS part and this column is of RHS part. So both the columns are same now. So we can say the theorem is proved. So you have to write the conclusion. So you write that here the columns x plus of y plus z is identical with x plus y plus z, hence theorem is proved. Okay. So the next part is, let us see the circuit construction for the given theorem. So left side is x plus into bracket y plus z. So three variables are there. One is x, second one is y, third one is z. So first we will go for this part. OR operation between y and z means OR gate. So this is going to be OR gate for y and z. So here the result is y plus z. So this one, what we are doing, this value, this output of this gate, we are taking an input for the further expression. Okay, so here what happens, this y plus z result is OR with x, OR in the sense OR operator. Okay, so now this is going to be the final expression, x plus, because this line is coming straight to the OR gate, so this line is identified as x, whereas this line is the result of this gate. So what is the result of this gate is y plus z. So one line is x, the other line is y plus z. So this is circuit construction for the LHS part. So now we will consider the RHS part. So RHS again, okay, three variables x, y and z. First we will go for x plus y here because of the bracket. So between x and y, OR gate between x and y. So x plus y. This is going to be an input signal for the next level gate. For the next level gate, this value is OR with z. So OR means it's an OR gate. Okay. So for this, the input is z. So here what you can write, it's about x plus y one side, OR gate, this z another side. So this is circuit construction for the given theorem. Okay. So in the same way, we have to go for the next theorem. So here instead of OR operations, we are having AND operations. So I will explain. So you would try to solve it. So I will leave this one as homework for you people. So what you can do, instead of plus you write dot here in when it comes to prove by perfect induction. So you can use the theorem of property of 0 and property of 1. Okay. Then we are going to get, of course, as LHS is equals to RHS in both the cases. Then it is about the proof by perfect induction. When it comes to truth table, again this is same. You consider three variables x, y, z. So you write all possible cases. Then you go according to this. First you consider y into z here instead of y plus z, y into z. Next is going to be x within the bracket yz here. Then it is going to be x into y. Okay, this one. Then finally x into y into z. Okay, so no doubt you are going to get two identical columns. Then you can say it is true. When it comes to gate representation, instead of OR gate, you use the AND gate. Okay, the capital D symbol. So easily you can prove the 13th one, quite similar to the 12th one. So still we are having some theorems. Overall we are having 18 theorems. Okay. So in the next class we will see the remaining theorems.